to teach you an encoding format for text that uses two sets of 4 bits to represent the characters A to Z and space in lowercase. So, 4 bits has 16 different varieties. That is, if you have 4 bits and you have to flip through all the states that are different, there's going to be 16 different states. So, how do you fit the whole alphabet in? The thought is this. The first set encodes the first half of the alphabet, and then there is an escape character. And when the escape character is hit, the token that comes next as the 4 bits that is after the other 4 bits that already was, this one will then count differently. It will be read as if part of set B, which then contains the continuity of the alphabet on the other side. And it itself also then, as the set B, has an escape code. So it's kind of like a tape, like one of those 80s things where you put the little cassette in and then you flip it around and then there's more on the other side. So in that sense, this is an escape-based encoding that resembles some of the earliest telegraph stuff and like the 5-bit punch card computers as well in a later period. Yeah. So let's just rehash. That is, you have a set of tokens. Each token is 4 bits, and there's an escape mode, which makes the next token count differently than the one before. And when the escape token is then seen again as the one from the second set, it returns into the mode for the first set. And so in this way, some of the characters will cost more because of the sort of the escape tollgate. You have to say that you're transitioning into the other mode to get access to the other half of the alphabet. So it's expensive for a lot of between half of alphabet distributions. So it also can be optimized by using an alphabet order that is most apposite for remaining in one half of the alphabet at a time, minimizing the amount of transition overall. And in that sense, it offers a compressive opportunity compared to the standard, which uses 1 byte per character. That's 2 sets of 4 bits for a single character, whereas we will, in a lot of the cases, a lot of the time, be using only 4 bits per character with marginal costs for the transitions in escapes. This means that you can use a smaller channel and still get the wide information through. It just takes more steps. Yeah. But also not overall. It's like the size of a step is smaller. So yeah, it takes more steps, but the size of a step is smaller than having to use then 2 steps at once and call it 1 step in the representation, which is a character per byte. Yeah. Okay, so them's my 3 cents. The thing is that the 2 4-bit spaces together actually makes a 5-bit space, and the alphabet is 26 characters plus space, that's 27. So then there's also the 2 escapes that we used that gives us 29, and that means that 30, 31, and 32 are open still to be used for escape codes or functional tokens that do something like in a scripting language. In that sense, there's further compressive opportunities when the escape codes that are extra are assigned to, for example, a dictionary space in which the tokens from that space counts for replacements that will be longer than the token. And that way you can have further compressive advantage from an interesting encoding.